Hello and welcome to Math Zone African Motives. In this tutorial, we will be working through a series of problems involving gradients, intercepts, sketching graphs, determining domain and range, symmetry, inverse functions, and equations of lines. We'll tackle these questions step by step, ensuring every part is explained thoroughly. By the end of this video, you will be more confident in your ability to analyze and work with various types of equations and their graphs. Let's begin with our first problem, question 3. The question is, given the equation 15x equals 5y minus 20. Let's read that again. Given the equation 15x equals 5y minus 20. In part 3.1, we are asked to determine the gradient, the y-intercept, and the x-intercept of the graph described by this equation. To find these properties, it's best to first rewrite the equation in the standard gradient-intercept form, which is y equals mx plus c. Let's recall what each part means. M represents the gradient, which tells us the steepness of the line, and C represents the y-intercept, the point where the line crosses the y-axis. The standard form is y equals mx plus c, where m is the gradient and c is the y-intercept. So our first task is to rearrange the given equation, 15x equals 5y minus 20, into this standard form. This means we need to isolate the y term. We have the equation 15x equals 5y minus 20. First, let's get the y term on one side. We can add 20 to both sides of the equation. This gives us 15x plus 20 equals 5. Now, to isolate y, we divide the entire equation by 5. So 15x divided by 5 is 3x, and 20 divided by 5 is 4. This leaves us with y equals 3x plus 4. Great! The equation is now in the form y equals mx plus c. We can easily identify the gradient and the y-intercept. Comparing our equation, y equals 3x plus 4 with the standard form y equals mx plus c, we see that the gradient m is 3 and the y-intercept c is 4. So the y-intercept is the point as 0, 4. We've found 2 of the 3 things we need. Now for the x-intercept. The x-intercept is the point where the line crosses the x-axis. At this point, the y-coordinate is always 0. So to find the x-intercept, we set y equal to 0 in our equation. We have 0 equals 3x plus 4. Subtracting 4 from both sides gives 4 equals 3. Dividing by 3, we find that x equals negative 4 over 3. The x-intercept is therefore negative 4 over 3, 0. To summarize our findings for 3.1, the gradient is 3. The y-intercept is the point, 0, 4, and the x-intercept is the point, 4, 3, 0. Let's write these down clearly. Here's the final answer for question 3.1. The gradient, m, is 3. The y-intercept is 0, 4, and the x-intercept is 4, 3, 0. Moving on to part 3.2, we are asked to sketch the graph of the line. We can use the intercepts we just found to make an accurate sketch. We know the line passes through 2 key points. Plotting these 2 points on a Cartesian plane is enough to draw the entire line. We have the y-intercept at 0, 4, and the x-intercept at 4, 3, 0. Let's plot these. Let's draw a set of axes. We'll mark the point 0, 4 on the positive y-axis. Then we'll mark the point 4, 3, 0 on the negative x-axis, which is approximately 1.33 on the x-axis. First, we plot the y-intercept at positive 4 on the y-axis. Then we plot the x-intercept at approximately 1.33 on the x-axis. Now, we simply draw a straight line that connects these 2 points. Let's make sure our line is labeled with its equation. Here's the sketch. We have the 2 intercepts clearly marked, and the line is drawn through them. The equation of the line, y equals 3x plus 4, is also shown. This sketch visually represents the linear function we've been working with. It's a straight line with a positive slope, meaning it goes up from left to right. Next, in parts 3.3 and 3.4, we need to state the domain and range of the graph. Remember, the domain of a graph is the set of all possible x values for the points on the graph. The range is the set of all possible y values. Domain is the set of all x values and range is the set of all y values. Let's look at our line y equals 3x plus 4. Arrows at both ends of the line indicate that it extends infinitely in both directions along the line. Here's our graph again. The line has arrows, showing it continues forever. Consider the x values. Because the line extends indefinitely to the left and to the right, it will eventually take on every single x value. There are no restrictions on what x can be. This means the line covers every possible x value on the number line. So, the domain is the set of all real numbers. The same logic applies to the range. Because the line extends indefinitely upwards and downwards, it will eventually take on every single y value. There are no restrictions on what y can be. Therefore, the line covers every possible y value. The range is also the set of all real numbers. Question 3.5 asks, is the graph symmetrical about any of the axes? Let's recall what symmetry means. A graph is symmetrical about an axis if you can fold the plane along that axis and the two parts of the graph line up perfectly. We're asking if the line y equals 3x plus 4 can be folded along the x-axis or the y-axis and have its halves match. Visually, we can see that it's not symmetrical about either axis. If we fold it along the y-axis, the points do not line up. If we fold it along the x-axis, they also don't line up. The only exception for a linear graph would be if it passed through the origin. Since our line has intercepts at 0, 0, 4, and so 4, 3, 0, it does not pass through the origin. Therefore, it has no symmetry about either the x-axis or the y-axis. So the answer to part 3.5 is no, the graph is not symmetrical about any of the axes. Our final part of question 3.6, asks us to find and sketch the inverse function. The process to find an inverse function is straightforward. Switch the x and y variables, and then solve for y again. This new equation for y is the inverse function. The graph of an inverse function is always a reflection of the original function across the line y equals x. Let's list the steps. First, swap x and y. Second, solve for the new y. And third, sketch the reflection. We start with our original equation, y equals 3x plus 4. Step 1, swap x and y. This gives us x equals 3 plus 4. Step 2, solve for the new y. Subtract 4 from both sides. X minus 4 equals 3y. Then divide by 3. Y equals x minus 4 all over 3. We can also write this as y equals 1/3 x minus 4/3. This is our inverse function, and we can call it y inverse. The inverse function is y equals 1/3 x minus 4/3. Now, let's sketch it on the same axis. We can find the intercepts of the inverse function. The y-intercept is -4/3, and the x-intercept is 4. Notice how these are the swapped intercepts of the original function. We also need to draw the reflection line, y equals x. Here is the combined sketch. The original line, y equals 3x plus 4, is shown. The dashed line is the reflection line, y equals x, and the red line is our inverse function, y equals 1/3 x minus 4/3. You can clearly see it's the mirror image of the original line. Let's move on to our next problem. Question 4. We are asked to sketch a graph. The question is, sketch the graph described by this equation. X over 4 minus y over 3 minus 1 equals 0. This equation is a linear equation in a slightly different form. Let's rearrange it into the standard y equals mx plus c form to find its gradient and y-intercept. We have the equation x over 4 minus y over 3 minus 1 equals 0. Let's isolate the y term. We can rearrange the equation to have y over 3 on one side, while y over 3 equals x over 4 minus 1. To get y by itself, we multiply the entire equation by 3. This gives us y equals 3/4 x minus 3. Now that it's in the form y equals mx plus c, we can see the gradient, m, is 3/4, and the y-intercept c is -3. Just like before, we'll find the x-intercept by setting y equals 0. So 0 equals 3/4 x minus 3. This means 3/4 x equals 3, and solving for x gives us x equals 4. The x-intercept is 4, 0. Now we have our 2 points, 0, 3, and 4, 0. Let's sketch the graph by plotting these points and drawing a line between them. Next up is question 5, which deals with straight lines and perpendicularity. The question is, determine the equation of a straight line that is perpendicular to the line 2x minus 2e equals 2 and passes through the point -1, 5. A key concept here is the condition for perpendicular lines. If a line with gradient m1 is perpendicular to a line with gradient m2, then the product of their gradients is -1. This is a crucial rule for perpendicular lines. The rule is m1 multiplied by m2 equals -1. So our first step is to find the gradient of the given line. 2x minus 2y equals 2. We'll call this gradient m1. To do this, we need to put the equation in the y equals mx plus c form. We rearrange 2x minus 2y equals 2. Subtract 2x from both sides to get a 2t equals 2x plus 2. Then divide by 2 to get y equals x minus 1. The gradient, m1, is the coefficient of x, which is 1. Now we find the gradient of the perpendicular line, m2. Using the rule m1 times m2 equals 1, we have 1 times m2 equals 1. This means m2 equals 1. So our new line has a gradient of 1 and passes through the point, so 1, 5. Now we can use the point slope formula for a straight line. This formula allows us to find the equation of a line if we know its gradient and one point on the line. Substituting our values, we get y minus 5 equals 1 times the quantity x minus -1. Which simplifies to y minus 5 equals 1 times the quantity x plus 1. Distributing the 1 gives y minus 5 equals x minus 1. Adding 5 to both sides gives us our final equation. Y equals x plus 4. Let's check the memo. The memo gives y equals x plus 4. Our answer is correct. The equation of the perpendicular line is y equals x plus 4. We've reached question 6, which introduces a new type of graph. Let's analyze it carefully. The question is, given the equation 5x squared minus 125 equals 5y squared. First, for 6.1, we need to sketch the graph. This equation involves both an x squared and a y squared term. Let's rearrange it to see what shape it represents. To identify the conic section, we want to group the x and y terms on one side. Let's start with 5x squared minus 125 equals 5y squared. By adding 5e squared to both sides and adding 125 to both sides, we get 5x squared plus 5y squared equals 125. Now we divide the entire equation by 5 to simplify it. This gives us x squared plus y squared equals 25. This is the standard form of a circle centered at the origin. Let's recall the formula for a circle. The equation of a circle centered at the origin is x squared plus y squared equals r squared, where r is the radius. Comparing our equation, x squared plus y squared equals 25, with the standard form, we can see that r squared equals 25. Taking the square root of both sides, we find that the radius, r, is 5. So the graph is a circle of radius 5, centered at the origin. To sketch it, we can mark the points positive and -5 on both axes and draw a smooth, round curve through them. Here is the sketch. We have a circle with its center at 0, and a radius of 5 units. Let's continue with the analysis of our circle. Part 6.2 asks whether the graph is continuous or discontinuous. Is the graph continuous or discontinuous? Continuity in a graph means you can draw it without lifting your pencil. In other words, there are no breaks, gaps, or holes. Looking at the circle, it's a single, unbroken curve. You can trace its entire path in one continuous motion. Therefore, the graph of a circle is continuous. So the answer to 6.2 is continuous. The circle is one solid piece. Part 6.3 asks for the range of the graph. As we discussed before, the range is the set of all possible y values. Looking at our circle, its center is at y equals 0, and its radius is 5. The lowest point on the circle is 5 units below the center, at y equals 5. The highest point is 5 units above the center, at y equals 5. The circle covers every y value in between these 2 points. Therefore, the range is all real numbers such that -5 is less than or equal to y, which is less than or equal to 5. We write this using set builder notation as y r to 5 equals y equals 5 yr. Finally, part 6.4 asks, is the graph symmetrical about the x-axis? Let's think about folding the graph. If we fold our circle perfectly along the x-axis, the top half would lie exactly on top of the bottom half. The shape is identical on both sides of the axis. This means, yes, the graph is symmetrical about the x-axis, and in fact, It's also symmetrical about the y-axis and even the origin, but the question only asked about the x-axis. Now we're at question 7. This question asks us to sketch 2 more graphs. Part 701 is the graph of y equals the square root of 18 minus x squared. The square root sign is a strong hint. Let's try to get rid of it by squaring both sides of the equation. If y equals the square root of 18 minus x squared, then squaring both sides gives us y squared equals 18 minus x squared. Now, let's rearrange this to get x squared plus y squared equals 18. This is the equation of a circle, just like in the previous problem. However, there's a crucial difference. Our original equation was y equals the square root, and the square root symbol represents the principal or non-negative root. This means that the y values must always be greater than or equal to 0. The condition y must be greater than or equal to 0 tells us we are only sketching the top half of the circle. The circle x squared plus y squared equals 18 is centered at the origin, and its radius, r, is the square root of 18, which is about 4.24. So, we sketch the semicircle that sits on top of the x-axis. Here's the sketch. It's a semicircle with a radius of the square root of 18, lying entirely in the upper half plane. Let's check the memo. The memo shows the graph of a semicircle in the upper half of the plane, and our sketch matches this perfectly. The center is at the origin and the radius is the square root of 18. Let's move to part 7.2. The question asks us to sketch the graph of x equals negative square root of 25 minus y squared. This problem is very similar in structure to 7.1. It also involves a square root, which means we can anticipate a part of a circle. Let's start by isolating the square root and then squaring both sides. We have x equals negative square root of 25 minus y squared. Notice the negative sign in front of the square root. This is important. Let's square both sides. When we square both sides, negative squared is positive, so x squared equals 25 minus y squared. Rearranging this gives us x squared plus y squared equals 25. This is the equation of a full circle centered at the origin with a radius of 5, just like the one in question 6. Now we must go back to the original equation and interpret the negative square root. The original equation states that x is equal to the negative square root of a quantity. This implies that x must be less than or equal to 0. We are looking for the x values on the circle that are non-positive. The condition x must be less than or equal to 0 tells us we are only sketching the left half of the circle. So we'll take our circle of radius 5, x squared plus y squared equals 25, and only keep the part that is to the left of the y-axis. Here's the sketch. It's a semicircle with a radius of 5 lying entirely to the left of the y-axis. We've arrived at our final problem, question 8. Let's tackle it. The question is, given the equation 25i squared minus 400 equals 16x squared. In part 8.1, we are asked to sketch the graph. Again, we have both an x squared and a y squared term. Let's rearrange the equation to see what shape it is. We want to bring the x and y terms to the same side. Starting with 25i squared minus 400 equals 16x squared. Adding 16x squared to both sides and 400 to the other side gives us 16x squared plus 25i squared equals 400. This is not a circle because the coefficients of x squared and y squared are different. This is the equation of an ellipse. To put it in standard form, we divide the entire equation by 400. 16x squared over 400 simplifies to x squared over 25. 25y squared over 400 simplifies to y squared over 16. This gives us x squared over 25 plus y squared over 16 equals 1. The standard form for an ellipse centered at the origin is x squared over a squared plus y squared over b squared equals 1. In our equation, a squared is 25, so a is 5. B squared is 16, so b is 4. Since a is greater than b, the ellipse is horizontally elongated. This means the ellipse extends 5 units in the x direction and 4 units in the y direction. The x-intercepts are at 5, 0 and 5, 0, and the y-intercepts are at 0, 4 and 0, 4. Here is the sketch of our ellipse. It's a smooth oval shape, stretching further horizontally than it does vertically. The memo confirms that the graph is an ellipse, centered at the origin with semi-major axis 5 and semi-minor axis 4. Let's complete our analysis of the ellipse. Part 8.2 asks, is the graph a function or a relation? Is the graph a function or a relation? To determine if a graph is a function, we use the vertical line test. If you can draw any vertical line that crosses the graph at more than one point, it is not a function. It's a relation. Looking at our ellipse, if we draw a vertical line, say at x equals 2, it crosses the ellipse at two different y values. This means one x value corresponds to two y values. Because it fails the vertical line test, the graph of an ellipse is not a function, it is a relation. So the answer to 8.2 is relation. Part 8.3 asks for the domain of the graph. As we established earlier, the domain is the set of all x values in the graph. The ellipse stretches from x equals 5 to x equals 5. It takes on every x value in this interval. Therefore, the domain is the set of all real numbers x such that -5 is less than or equal to x, which is less than or equal to 5. In interval notation, this is 5, 5. Finally, part 8.4 asks, is the graph symmetrical about both the x and y axes? Yes, an ellipse centered at the origin is symmetrical about both axes. If you fold the ellipse along the x-axis, the top and bottom halves match perfectly. The same is true if you fold it along the y-axis, the left and right halves match. This can also be seen mathematically. The equation x squared over a squared plus y squared over b squared equals 1 contains only squared terms. Replacing x with x or y with y doesn't change the equation, which is the test for symmetry. So the answer to 8.4 is yes, it is symmetrical about both axes. And that concludes our tutorial. We have successfully worked through a variety of problems, including linear functions, their inverses, gradients, intercepts, and different conic sections like circles and ellipses. We learned how to convert equations to standard forms, interpret their features, and sketch them accurately. We also practiced finding domains and ranges and testing for symmetry and function properties. Mastering these concepts is a fundamental step in your mathematics journey. Keep practicing and applying these skills to different problems. Thank you for joining this Math Zone African Motives tutorial. If you found this helpful, please remember to subscribe for more tutorials. We'll see you in the next video.